So today I will discuss about the different reliability analysis methods used in statistics, and I will also try to give an idea of reliability. What is reliability index? What is probability of failure? And what is the difference between reliability and validity? So in this short presentation I will try to explain all these important concepts which are very essential if you want to do some statistical analysis on the performance of system, performance of a machine, performance of some procedure. You need to know these concepts. Now, first is what is reliability analysis? Reliability analysis is actually it indicates how reliable or consistent a system is. By consistent I means if this is our say for example, if this is our if this is our if this is our profit and if this is our loss, then if the relationship in between these two is like this, it must remain like this for a longer time span. Suppose from 0 to t, this is the relationship. But after t to t1, if the same relationship exists, then you can say from 0 to t1, this system or this business is reliable, and the relationship in between profit and loss is or can be represented by this curve. Or if you draw a straight line, the equation of this pattern will represent the relationship between profit and loss of a business, which is reliable at least within the time scale 0 to time scale t1. But if the system behaves like this, then so this is not a reliable system because it is changing its behavior with time in the same time span. So many patterns. So these type of systems are unreliable and also very hard to predict. Reliable systems are very easy to predict, but unreliable systems are very hard to predict. That is why before developing a model, one of the most important steps is to find out whether a system that we want to model or we want to predict, suppose we want to predict the profit with the help of this loss. So before developing a model with before developing a model whereon if I give the loss, it will give the profit, we must see that within a time span, the relationship or interrelationship between the profit and loss is stable. It doesn't change. It doesn't change means the pattern of the profit and loss does not change. Okay, within a specific time span. Then we can say that this system is reliable and we can develop a model of this system. But if the system is unreliable even in this time span 0 to t1, then it will be very hard to develop a model based on this system. So this is why we do a reliability analysis before developing a model, and or before developing some plan to improve the profit of this system, or uh, to analyze the performance of this system. We need to know how reliable is the system, right? We can take another very easy example. Suppose for a certain watershed, if we check the relationship between rainfall and runoff, okay, suppose this is rainfall and this is runoff, then suppose in 1 year, if the pattern is like this, then you can say that the system is reliable. Although for a more consistent analysis, you must take the data of at least 5 years or 10 years, and if within those years, if the pattern does not change, it remains as it is, then we can say that the relationship between rainfall and runoff for this watershed is stable, is reliable, and we can develop a model based on this data. However, if the relationship between rainfall and runoff, sorry, if we take this as rainfall and take this as runoff, then it is more accurate. And if it varies like this for first year, this is the relationship. In the second year, you see more than 2 peaks. In the third year, it is like this. In the fourth year, this is like this. Then it will be very difficult to model this watershed, because the relationship between the precipitation and runoff is not stable within the time span, right? So if the interrelationship between two variables is stable, is consistent for a specific time span, then it is said that this system is reliable. And how to conclude whether the system is reliable or unreliable? For that, we need to learn different method of reliability, right? Now, let us say what is reliable system. These I have already discussed. Okay, so next let us discuss about the different types of reliability analysis methods. Here you see already I have discussed about this test retest reliability analysis method. It is similar to the that consistency within a time span case type of reliability. So in this test retest, what happens is they take data of suppose precipitation and runoff for suppose let us say 5 years, and if the interrelationship between P and R remains same within the span of 5 years, then it is assumed that this data has high reliability. So how to identify that the relationship doesn't change within these 5 years? For that, we calculate the correlation coefficient or R square in between the data of precipitation and runoff for 5 years. Now the limitation of this system is it may happen that after 5 years, this relationship may change. And at that juncture, even if for 5 years, this test-retest method shows that the data of precipitation and runoff is reliable, but if we consider 6 years instead of 5 years, then this relationship may change. So that is an inconsistency about the test-retest method. In case of internal consistency reliability method, here we uh, calculate a score and we rate a system based on some factors or variables. Factors or variables, and based on the rating, we give a score, suppose out of 100 or out of 50 or out of 10. And by the way, when several items are rated, suppose what I can say, suppose the performance of the system for suppose January, April quarter, and the performance of the same system for May, August quarter, and then September, December quarter. So for these 3 quarters, if I rate the performance of the system with the help of different factors and variables, and I rate them with the help of a score out of 100 maximum point or 10 maximum point or 50 maximum point, and then if I compare the score in between Q1, Q2 and Q3, and if it shows average score, or if it shows similar scores, then we can say that this system is reliable throughout the year, throughout these 3 quarters. But if suppose for Q1 I have only 20 out of 100, say, and if this is 70 out of 100, and if this is 60 out of 100, then this Q2, Q3 ratings are okay, similar and reliable, we can assume. But 20, the rating of Q1 has a high variance from the rating of Q2 and Q3. So in case of Q1, the performance of the system is not as expected, or not as good as the performance of the system in Q2 and Q3. So if I compare Q1, Q2, Q3, the system becomes unreliable. Okay. And similar to this system, there is another one. It is known as split half reliability. So here what happens is, here the entire time span, or what I can say, the entire scale are divided into 2 parts. And suppose for the same system that I was discussed in the earlier case, suppose we divide a year into 2 halves. Say for example, first 6 months, January to June, and the second 6 months, that means July to December. And if I again rate the system for January to June and July to December, and if I find for this is 70, for this is 65. So both these rating, or 2 halves of the annual financial year, both these two have a high correlationship. This is 70, this is 65. So then we can assume that the system is reliable. But if suppose this is plus 70, this is, say for example, this is 70, and this is, say, only 5. Okay, so if this is only 5, then it becomes an unreliable system because the ratings of first half varies significantly from the rating of the second. So this is what is split half reliability analysis. But however, this system has also some limitations. Limitation is how we will divide the scale. I have divided into 6 months, 6 months. Now if I divide it into 4, 4, 4, then the conclusion can be different. If I divide it into 6 half of 2 month duration, then also the system will be may show some other result. Or if I divide the 1 year into 9 and say 3, then also conclusion can be different. So it depends on how we divide the scale, and based on the division, the conclusion may change. And lastly, this is integrated reliability. I have already discussed about it. When few people, more than one people rate a system, a product, or an item, and if all of them rate the product or systems in a similar rating, then the system become reliable. And if they give, some are rating it highly, some are rating it very poorly, then all the ratings are not reliable to show the performance of the system. So that much about the different type of reliability analysis method. Now come to the very important point. This is your uh, reliability index. What is reliability index? Yes. What is reliability index? Now, reliability index also shows the reliability of a system based on some safety factors. So, take the example of a business house. The safety factor of the business house can be its profit, can be its loss also, can be its income, can be its expenditure. So there are various factors on which you can analyze a system to know how the system is performing. So here the formula is like this: beta, which is the reliability index, mu is the mean of the factor that you have chosen, the mean of the data of the factor collected from a specific span of time. Suppose the income of an entirety of a business house for the last 5 years. Then the mean of income, which is derived from this 5 years data, will be this one, mean. Minus 1, this is the critical factor, or this is the reference frame with which the mean of the safety factor is compared. And this is the standard deviation. It shows how many standard deviation difference exists in between the mean of the safety factor and the critical factor. So for example, if the mean is 3 and safety factor is 1 and standard deviation is 1, then reliability index will be 2 and it indicates high reliability. More the reliability index, more reliable will be the system. Now remember, factor of safety can be anything, and it will depend upon the decision maker or analyzer to identify what variable or what factor he will consider as the safety factor. Okay, so let us go to the next one. These I have already discussed, right? One thing you must note is when reliability index is 0, it implies that mean factor of safety is also 1. So actually it implies that the mean of the factor of safety is equal to the critical factor. So the reliability index is 0 in this case, which shows not a very highly reliable system. Okay, and of course, if there is negative reliability or negative reliable index, then the system is highly unreliable. So whenever beta is more than 0, system is reliable. When the beta is less than 0, system is unreliable. And when the beta is equals to 0, here also it indicates that mean of factor of safety is equals to critical factor, and which indicates that it is a neither reliable nor unreliable system. So majorly, or in practice, when beta is 0, it is assumed that the system is unreliable, because if mean of safety factor is nearer to critical factor, it indicates unreliability. Okay. Now, yes, one thing I have forgot to tell you in the earlier case, when we are calculating beta is equals to mean minus 1 standard deviation, then we are assuming that the data from which this mean and standard deviation is calculated, data of the safety factor, this is normally distributed. But whenever the data is log normally distributed, then we have to use log normal reliability index, which is given by this log of mu of the safety factor divided by root over 1 plus variance of the safety factor square divided by root over log of 1 plus square. Now here you note the base of this log is 10, that is log normal, and as we are taking log, no term of the data series, no term of the data series, that means if this is a data series 1, 2, 3, 7, 9, if this data series represent the safety factor, then none of the term must be negative. If it is negative, you cannot use log normal reliability index. Okay. So, in case of log normal distribution, the data of the variable must always be positive. Okay. So, as I have already discussed this, yes, now the very important thing, what is the difference between reliability and validity? Reliability, I have discussed so much. What is reliability is? It is mainly consistency. Consistency of a measurement, consistency of a scale, consistency of two different items, consistency of rating. This is reliability. But validity refers to whether the study or measuring test is measuring what it claims to measure. If a study is measuring the rainfall, then it must not measure temperature. If a study is measuring temperature, it must not measure evaporation. So a study must measure what it desires or it promises to measure. So that analysis is known as validity analysis. And reliability analysis is the consistency of that measurement. Right? Now, other than all those four methods that I have already discussed, test retest, then integrator consistency, then speed up reliability, then again rating reliability, raters reliability, there are other methods of reliability analysis. So there is one form method, first order reliability method, another one is second order reliability method. Now I will just discuss how you can do this, how you can uh, analyze the reliability of a system with the help of form or SORM method. Now, In case of SORM method, let us say, suppose in a hydropower dam, in case of hydropower dam, the mm, let us say there is a load, that means a demand of the hydropower dam, and there is a capacity up to which a hydropower dam can supply. Let this capacity be resistance, term as a resistance, and let this load be what I say. Let it be load or supply. Yeah, you can say it as supply. Now, if I have the data of this load and capacity for 6 months, the runoff data or the discharge data, or let us take the discharge data. Okay, so the demand for the power which a discharge can generate. Suppose if I want to say that I want 10 kilowatt of power, then how much discharge is required to create this power? That can be found with the help of this equation rho g q h meter. This rho is known as density of water or the fluid. G is acceleration due to gravity, and this q is your discharge, this h is your head, and this neta is the efficiency of the turbine and generator, which the kinetic energy of the water is rotating to generate power. So here I am taking that how much discharge is required to generate this load. Suppose my demand is 10 kilowatt, so how much discharge is required to generate this demand, right? So let us say Q is 10 cubic, 25 cubic, 75 cubic. As you know, the unit of discharge in SI is cubic. 10, 25, 75, 120, 150. Let us say this. That means this amount of discharge is required to supply the demand of power from this hydropower plant. However, the capacity of the hydropower plant is to generate a power which can be generated by a discharge which is equal to, say for example, 75. Right? That means this power plant or hydropower plant has a maximum capacity to cater 75 cubic of discharge. This is the maximum. More than that, it cannot. It cannot generate or cannot supply that power. Okay? Now, to know or to analyze that whether this hydropower plant or hydropower system is reliable or not is, the first step is, what you will do is, look here in case of P, it is in case of capacity or in case of resistance, this is same, this is 75, this you cannot change. But in case of load or supply, you can change because in different month, different supplies were demanded. So, what we'll do is, we'll rank this discharge in descending order, where the maximum discharge will have the best rank. That means this 150 will have the best rank, followed by 120, then this then this, then this. That means this will be awarded the first rank, second rank, third rank, fourth rank, fifth rank. Then, so what it will be like this. This is 10, this is 25, this is 75, this is 120, this is 150. Okay. Now, with the help of the formula of plotting position, that means P is equal to m by n plus 1, to calculate the probability of this, the probability of the discharge 10, 25, 75, etc. We use the formula P is equal to m by n plus 1, where m is the rank, n is the number of data point, plus 1 means you just increment it by 1. So this formula will give the probability of these discharges. Suppose this 10 is have a rank of 5, so it will be like this: 5, 5. There are 5 data, 6. So this ratio will give you the probability of this discharge. Okay. Now, after finding the probability of all these discharges, what we'll do is we'll use this. What I would say. We'll use this formula to find out the beta. This beta is the reliability index, and then with the help of this beta, we'll find out the probability of failure, PF, probability of failure, which will show the probability of the failure of the hydropower plant based on the data we have. So what we first will do, this is beta. We'll calculate the beta. Beta is the mean of this factor. This is also your safety factor, and this safety factor, or we here we say it as a random variable Z, which is a function of both resistance and supply. So this is actually what we say is, if Z is equals to R minus S, and if this Z become less than 0, then failure will occur. So probability of Z will also show the probability of failure, right? Now what I will do is, we will find this beta first, mean of Z divided by standard deviation of Z. So this is what we will find is mu R minus mu S divided by root over standard deviation of R plus standard deviation of S square. Here what we do is, we find the beta. So this is mean of resistance. Now as you can see that there are only one data of resistance. You can straight away give it 75, right? And there is supply. There is 5 data points for supply. So for each data point, for example, the data points are like, I think, 10, 25, 50, then 75, and then I think 120, like this. So for each data point, you have to calculate the beta. Okay. So how to calculate? Mu R resistance is always 75 kΩ. So 75 minus 10. No, not 10. This is 75 minus mean of this sample data points. So I have said it incorrectly that you have to find out beta for each of the data point. It is not like that. You have to find the mean of this data series. So let us say the mean of this data series is 50, and then you divide it and you find the square root of the summation of standard deviation of the resistance. So as you can see that there is no deviation because there is only one data, and standard deviation of this S, that means standard deviation of this series. So basically this become sigma S. So this will give you the beta, and when you deduct beta from 1, then you get the probability of failure. And you can see that when beta is less, probability of failure is more. When beta is more, probability of failure is less. Suppose when beta is 0.89, then your probability of failure is, I think, 0.11. So very low probability of failure. But when beta is only 0.1, then your probability of failure becomes 0.9. So when beta is lesser, probability of failure is more. When beta is higher, probability of failure is lesser. So to summarize it again, now you will say why we have found out that probability in the earlier slide. What is the use of it? Yes, what is the use of it? When someone says that calculate the probability of failure of a system, then there is no need to calculate the probability of each of the data. Okay? But when someone says that calculate the probability of failure of this system with the help of your first order reliability analysis method, SORM, then you have to find the probability of all these data points. So for the first step of SORM method, you have to find out the probability of each data point with the help of that plotting position formula. That means your m by n plus 1. Then the next step will be to use the beta to find the beta. But here when you calculate this mu r minus mu s divided by standard deviation of r plus standard deviation of s square, here this mu of resistance will be the probability of the resistance. That means if you have only one data as 75 cubic, then the probability of this data will be 1. So this mu of resistance will be the probability of the only data that is available for resistance. So this will be your 1. In the next step, this mu or mean of the supply or mean of the data available will be the mean of the probability of each data point which indicates supply. That means what we have done in the previous slide. So the probability of the mean of the probability of these data points, that means these data point converted into their probability, and then you find the mean of that. So this becomes your mean of probability of the supply data. So when you deduct this mean of probability of supply data from the mean of the resistance, probability of resistance data, divided by sigma r square plus sigma a square. This sigma r will be 0 as there is only one data, and the standard deviation here also, this standard deviation sigma a square will be the standard deviation of the probability of the supply data. Okay, so this probability of supply data sigma, the value the beta will give, and the probability of failure that will be found, that can be found out by deducting beta from 1. This will be your probability of failure, or this beta will be your reliability of the system based on the SORM method. That means when you calculate this beta with the data itself, then it is become probability of failure. When you calculate this beta with the probability of the data, then it becomes probability of failure by SORM method, or reliability analysis by SORM method. And next, we are coming for the SORM method. Now, in case of SORM method, okay. Now, in case of SORM method, you see what happens is we use the term moving average. So instead of using the probability of the data point, what we use is, suppose if this is the data point 10, if this is the data point, say 10, 20, 30, 50, right? Then what we find out is, we remain it as 10, but this become 10 plus 20, 30 by 2, average of these two data. But after then we come to here, this become 10 plus 20 plus 30, 30, 60 by 2, so by 3. So 30, 30, 60 by 3. So this is your 15, this will become 20. After then 10 plus 20, 30, 60, 110. 110 divided by 1, 2, 3, 4, 4. So this become what? I think this will become, I think 27.25, like this, right? So this 10, 20, 30, 50 data now will be transformed into its moving average, and the moving average will be ten, then 10 plus 20, 30 by 2, that means this will be your 15, so 15, then 10, 20, 30, 60 by 3, this will become 20, and then 10, 20, 30, 60, 110, 110 divided by 4, this will be, I think, this one. Okay, so these are all random point example points, so it can be some mistake can be there, but more or less this is what it is. Moving average of this data point is this, right? After that, you use the SORM method. That means you find the probability of these data points, right? You find the mean of the probability, then you put it into this equation, right? And then you find out the beta, and from beta you find out the probability of failure. So this is the basic difference between your form and SORM. In case of SORM, what you do is you find the moving average of the data point first, and then you find the probability of that moving average with the help of plotting position formula, and then you do the same thing as you do in the form method. You find the mean of the probability of those data, you put it into the equation, and then accordingly you find the probability of failure. And just note that in case of this, in case of SORM method, this mean of resistance will be 1, because if resistance is a single data, then this will be equals to 1. But if there is more than say one data, then you have to find the moving average of that data, and then you have to find out the probability of those factors, probability of those data from the moving average, and then you have to find out the mean of those data, and then you have to apply it into this new R. This is the mean of the data, probability of the data of the resistance. So if it is 1, very easy, just put 1. For form it is 1, for SORM it is 1. But if there is more than one data in case of resistance series, then you have to find the mean of R. By the same method, you find the mean of S by the SORM method. That means you have to first find the moving average of that data series, then you have to find the probability plotting. You have to find the probability of those moving average data points with the help of plotting position formula, and then you have to find the mean of R, right? So more or less, this is a very brief discussion on the reliability analysis and how to calculate it, what are the different ways you can calculate reliability analysis, how you can calculate the probability of failure, how you can calculate the reliability index in a simple method, and also by form and SORM method. In case of form method, in case of simple method of calculating reliability index and probability of failure, straight away find the mean of the data points available and put it into this reliability index equation and find the probability of failure, PF is equal to 1 minus beta. In case of form, you find the probability of each of the data points, and then you find the mean of the probabilities and the standard deviation of the probabilities, and then you put it into this equation, and accordingly you will find the beta with the help of form method. And in case of SORM method, you find the moving average of the available data point for the supply data, and then you find the probability of each of the points of that moving average with the help of plotting position. Then you find the mean of those probabilities and put it into that equation. If resistance data is single, that means mean of R will be 1 then. If the resistance data is more than 1, then you have to use the same method to find mean of R that you have adopted to find mean of S in case of form or in case of SORM, right? So more or less, in conclusion, this is a brief discussion on the reliability index and probability of failure calculation for a system, for a model, for a watershed, right? And this is an extremely important concept, because before developing a model or before designing a hydraulic structure, before designing a dam, we must calculate what is the beta reliability index and what is its failure, probability of failure first, and then we must, based on that data, based on the probability of failure data, we must go for the later calculations or for the further calculations, right? So with this, I will conclude this lecture. Thank you for listening.